All right, yes. So the recording has officially started, right? Um, right, so this is, what year was this? This is 2019 paper, basically, that you all got from mock exams. The first thing that we would have to do for this would have been to figure out what the expression was that was related to this so that we can draw the truth table for it. So we know that this is an AND gate right here. Okay, so we know that this is an AND gate and this is a NOT gate right after it. And so basically we taking the output of X and Y and we inverting it. Okay, so we'll end up with this. Okay, we'll end up with NOT X and Y. Okay, so not X and Y would be our circuit that we have to draw the table for. All right. Some of you all might have represented it like this, not X, Y. That's fine. Some of you all would have represented like this, not X and Y. Actually, you could represent it like this, not X and Y. That was fine. Right? Or you could have represented it like this. X. Okay, any variation in terms of for the second part where you had to put the expression, any of these variations would have been fine. So we want to construct the truth table. So we have, of course, the X value, the Y value, and we have all possible bit patterns, 1, 0, 1, 1, right? And that is allowing us to count up to from 0 to 3 in binary. Okay, so the first thing that we would have to do, hold on a second. Sorry about that. All right, so we have X and Y, and we have X and Y, and we know that the only way that we get a positive here is in the instance where both are true. So we end up with 0, 0, 0, 1. And then if we do in the not X and Y, right, we'll end up with 1, 1, 1, 0, which is just the inverse of the X and Y value. So this was the first question here. Most of you have handled that pretty well. Most of you handled that pretty well. Next. Okay, write the logic expression that represents the operation in the circuit. Okay, we just did that up there. So the logical operation would have been not X and Y, right? Or you could put X and Y with the not in there. Either one of these is fine, or you could even, I believe CXC would give it to you if you write it out like not X and Y, but the X and Y has to be in the bracket. You cannot write not X and Y. This is incorrect. This is not the same thing. Because what you're doing is that you're applying it not to the whole expression. So that's why you have to put the brackets around it. Okay? Okay. So draw a diagram of a circuit that can accept two binary inputs referred to as X and Y. The circuit should represent the propositional logic for not X or not Y. So again, most people, I think, did pretty decent on this because I corrected questions 1 and 2 so far. All right, you start off with X, you start off with Y. Now they want us to invert the value of x and y before passing it into the OR gate, right? So our OR gate looks like this, and we will take the value of x, and you have to invert the x value and pass it into the OR gate. And then you're doing the same for the y, right? You have to take the y value and invert it, and then it passes into the OR gate. And you will have your expression here, right? Which is not x or not y. Everybody good with this? Any questions?
No, sir. So we have to show the x, the not x plus not y on
Sorry?
diagram. If we have to show the not x,
yeah, it's recommended, or you could put like, you know, output value like f or d or something. So, you know, you don't have to put it. It's not like mandatory. But you know, I prefer to just see something at the on the output here. Okay.
okay.
Or what you could do is that you could, you know, if you wanna be like, you know, actually, then you could be like f is equal to that, and you could put f here. All right. All right. So the next one, describe the following of the following components, given an example of each in modern computer systems. So we have multiplexer. A multiplexer is what? Anybody could define a multiplexer for me?
It's an electronic switch that takes in multiple signals and it outputs a single signal.
Right. So it's a circuit that allows us to take in multiple input signals and through a value asserted on a select line, right? Via select lines, it allows those multiple inputs to utilize a single output line. Okay, so an example would be used in telecom to allow for multiple persons to talk on a phone system at the same time. All right, and a decoder is different from a multiplexer. Some of you kind of had an answer there that was kind of, you know, very much tying the two kind of together, but you know, a decoder is different. A decoder, and I was pleased to see some of you all that had this, right? A decoder has n inputs and 2 to the power of n, 2 not s, output lines. only one of which is asserted based on the pattern put into a decoder has n inputs and 2 to the power of n output lines, only one of which is asserted based on the pattern put into the fed into the input line. So an example of a decoder would be, it can be used, used to reference memory locations in RAM. Okay, and how is this possible? Right? Think about, let's say for instance, if we have a memory instruction. If we have a memory instruction, we might have an instruction, and this ties into another area of this Unit 1 syllabus that we will come across, right? Like instruction format and instruction size, etc. Let's say, for instance, we have an 8-bit instruction, which means that the instruction that goes into the processor could be anywhere from 8 zeros to 8 ones. Okay? Let's say, for instance, our 8-bit instruction is a 1 address instruction with 2 bits for the opcode. Right? So this is the opcode, and this is the address, 6 bits for address. So what does this tell me? This tells me that if I have a computer instruction like 0, 1, 1, 0, 1, 1, 1, 1, this could be the data that is being fed into the processor. Now, if I reserve 2 bits for the opcode, it means that I have a possible maximum of 4 instructions that I could execute. How did I get 4 instructions? Well, 2 bits could give me 0, 0, 0, 1, 1, 0, and 1, 1. So 0, 0 could be something like load. 0, 1 could be something like add. Right? 1, 0 could be something like move. Right? And 1, 1 could be something like subtract. That's it. I'm limited to 4 instructions, because only the first 2 bits of my instruction that comes into my computer system is associated with it's associated with some sort of memory address or location. Sorry, with some sort of memory instruction, computer instruction. Hold on, please. The curriculum officer for computer science calling me. I have to take this call. Yeah, sorry about that. All right. So we were at the point where we were talking about a computer instruction. If we take a simple 8-bit instruction, and we have if we take a simple 8-bit instruction, and we have the instruction split into the operation code, which is this part here tells the processor what to do. Okay, so based on the operation code, whatever code we could match. So basically we're saying add whatever data is in this address, right, to probably the last instruction loaded. Okay, and now if it is that we have 6 bits for the address, what does that tell us? 6 bits for the address could tell me that if I have 32 slots, right? If I have 32 slots, 1, 2, 4, 8, 16, 32, or sorry, if I have 64 slots in my memory, right? And just making sure that I'm not leading you all down the right road. So I just want to make sure that 2 to the power of 6, right? Yeah, 64. Okay, because this morning my brain working slow. Right? Let's say, for instance, we have memory here. So this is my memory locations, and I have different addresses in memory. Dot, dot, dot. And this is location 0, this is location 1, this is location 2, 3, 4, 5, dot, 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 up to 61, 62, and 63. This instruction here could be decoded to a particular memory location. This is location 1, 2, 4, 8, right, 16, 32. So 32 plus 8 is 40, plus 4 is 44, plus 3 is 47. Okay, so if we have location 47 somewhere here, when my computer sees this instruction here, it decodes it and knows that it can access the data at memory location 47. That's how decoding works. So basically, if my decoder had 6 inputs, right? 1, 2, 3, 4, 5, 6. It could have up to 64 outputs. Dot, 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 dot. Right? Where this would be output line 0, 1, 2, 3, 4. Right? This is 47. This is 61, 62, 63. So if my decoder has the value 101111 placed into it, the line 47 is going to be asserted. And that's how a decoder works. You all follow me here? So this was just an example of like, let's see how a decoder would work to reference a memory address. Everybody real quiet.
So this is the same decoder in the fetch, decode, execute cycle.
Yes, you could think about it as the decode process from the fetch, decode, execute cycle, right? Because this here is just thinking of a decoder as a standalone circuit. But if you're thinking about what the decoder does in general, it's the same process in terms of your fetch an instruction. So this is the instruction that was fetched from the instruction register. 01101111. We want to decode that instruction. We want to understand what is to be done with that instruction. we could break that instruction according to the processor's rules into an opcode and an address. The opcode is going to tell us what action the processor is going to take, and the address is going to say where we can get the data for that instruction. Understood? And where is the data stored on a computer system? The data is stored inside a memory. So when I pass an instruction in, and that instruction is not, again, we're dealing with an 8-bit system here, so it's a short instruction. If we have 6 bits, then it means that our memory is located to one of 64 locations. So that's why in 32-bit processing, we could have, let's say, for instance, if we have a memory address that could be, a little longer, 16 bits long or longer than that, if we have multiple addresses, then that gives us a wider range of memory that we can access. But just keep it small so that we could maintain it and think about it in an understandable manner. So if it is that the instruction is pulled and then it's passed through the decoder is going to say, okay, we are going to read this address here, right? This binary code that represents an address, and it will tell me exactly where, right? Or it will give me, if you want to use the line, it will give me like a direct line to accessing a particular location in memory. That's the decoding. So that once you access that data in the fetch, decode, execute cycle, you could now execute that instruction. Is that fine? Hello? Yes? No?
Yes, sir. I good.
Yes.
I understand.
All right. Okay. So, all right, we're moving on. Describe with the aid of a diagram how a 2 to 4 line decoder can be applied within a centralized gate opener system that manages 4 gates of an apartment complex. Now, what amazed me with this question is that some of you all did not really work out an example for decoder in the last question. Then they give you an example of how a decoder could be used in this question, and you all didn't even go back and put this example into the previous question to get full marks from the previous question. TXC basically gave you the answer to the previous question with this question. You all saw that?
So no shit.
So you have to look out for these things, because I know that sometimes when you're in exam mode, you're just thinking, yes, answer the previous question, go forward. Answer the previous question, go forward. Sometimes, and especially in this section, one thing could be related to another thing. And they could ask it in such a way that that previous thing can actually make you go back and get a little marked, right? So with the aid of a block diagram, how a 2 to 4 line decoder. So let's say we have our decoder here. Okay, our decoder here. And we have 2 input lines, and we have 4 output lines. And these 4 output lines go to different gates. So this goes to G3. This goes to G2. This goes to G1. And this goes to G0. Okay? Depending on the signal sent, from the transmitter, right? So the transmitter could send a signal here. We will assert a particular gate. So if I send a signal of 0, 1, right? So that 0, 1 comes in here. This will open gate 1. Because depending on the information coming into this decoder, it allows for a particular gate to be asserted. Okay, let's talk that out now. So we can use a decoder. We can use a decoder to each give the, not just give, the owner of each apartment gate a switch, right? Or let's say a remote that is encoded with values 00, 01, 10, or 11, right? Respectively. When the owner their remote, their signal is sent and it will open gate 1, gate 0, and it will open gate 0 for code 00, gate 1 for code 01, gate 2 for code 10, and gate 3 for code 11. Each remote signal is decoded to each remote signal, that's not how you spell signal, is decoded to assert the switch connected to a different gate. Now, I say this over and over and over like this so that you all could get an understanding of how this exactly works. Do you all understand how this exactly works now? Right? So in this example, the remote opens G1, right? In this example, the remote with code 01 opens gate G1. Does everyone follow? Yes? No?
Yes, sir.
Yes,
All
sir.
right. So you all see how simple and easy these questions are really? It's not that bad actually. Agreed? It's not that bad, right? Nobody wants to agree. Or worse yet, nobody wants to agree on a recording. Okay? All right. And then, right, describe how the program counter register is useful while a computer is executing a series of steps. What is the program counter? What is the program counter register for? Anybody? All right. So we know that the program counter allows a computer or allows a processor to keep a processor to keep track of all of the processes in the system that are yet to be executed. Right, the program counter basically lets the processor know what the next process to be executed is. So it keeps track of all of your instructions to be executed in your instructions to be executed in a computer system. Long and short, that's what it does. Okay? Agreed? Any questions?
No, sir.
Thank you, Alicia, for answering. All right. And I'm gonna call out Joshua's name as having said, yes, see, it's not that bad for the questions in terms of what is being asked, okay? All right. So state one reason why 2's complement representation is considered more suitable to represent integers in modern computers than sign and magnitude and 1's complement. There's actually 2 reasons that we can use, right? The main reason, and this is the reason that I would put, the main reason is that 2's complement, right? Only allows for one representation of the value 0. Okay, 2's complement only allows for one representation of the value 0. We do know that compared to sign and magnitude, you lose 1 bit to be able to represent the sign, and that causes a problem because, of course, now if you have 8 bits, the most that you could represent is 127 positive to negative, right? And you still get the problem of if it is that you have all zeros with the bit for all zeros being represented positive or negative, that's still a dual representation of the value 0, right? We know that once complement, you have 2 ways of representing 0 as technically like a negative and positive. All right, but 1's complement, sorry, that's a problem. 2's complement only allows for 1 representation of the value 0, and that's because of that consideration where you shift the bits. Okay. State the range of Iran.
Yes. So our answer couldn't be that is the most useful form of handling negative numbers because you could use all the bits.
That's not the main reason, but yeah, it is a reason, right? So I think I might have given you that, yes, because they didn't really say the main reason. They said like state one reason. So that's just almost exactly like what I said, as opposed to sign and magnitude. It allows for a greater range of negative and positive numbers. Okay. Hello?
Yeah, yes, sir.
Right. Right. So state the range of numbers that can be represented using 2's complement format with 16 bits. Right. I would have accepted this. 2 to the power of 16, right, is 65,536, I believe. Right, 536. So you could have put 535 because remember the 536 would be represented by the 17 bits, right? To 65,534. Okay. Or we would have been able to say, if you had done it like this, which is a little arduous to do, right? You could have drawn out the 16 bits, right? And say 0000 16 times to 11111 16 times. That would have been acceptable too, right? Or you could go 2 to the power of 16 minus 1 to negative 2 to the power of 16 plus 2, right? And I think that would be yes, right? So this would be a way of representing it too, right? 2 to the power of 16, which is 65,536 minus 1. Because again, if we have 16 bits, okay, right? If you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, okay? I just need you to kind of trust me on this one, that this would be equal to 65,535. This bit here, which would have been the 17th bit, would represent 65,536. So the biggest number that this group of digits could create is 65,535. Which is why you say you take the value that would have been at the 17th bit, you take the value that would have been at the 17th bit and you minus 1 from it. Do you understand where I'm coming from?
Yes, sir.
All right. Thank you. Thank you, that one guy who answered me.
So
And Joshua, who was about that. Yeah.
So why you have 65,535 to 65,534 is not like 1. So how does
Right. All right, because of the fact that remember your with your 2's complement, right? You would have added 1 to the value inside of here to compensate for the number of 0, right? So is it minus 65,536? I could never remember if it's forward 1 or back 1. So I would have to check it, okay, to make sure. So let me I will message you all in the group, and this is the minus, right? This might be minus 65,536 actually. So I would just have to check and verify that one, right? Because it might be actually 2 to the power of 16 minus 2 to the power of 16 exact. The adding of the 1, let's say we wanted to represent, no, it would be, I think it would be 65,534, right? Minus 65,535, this would be all zeros, right? Plus 1, so I will have to work it out for you, right? But it would be either 1 before or after this value. Okay, Joshua?
Yeah, okay.
All right, then. No problem. Derive the 2's complement representation of the decimal value minus 75. So this question here, this question kind of some people didn't show like the full working, right? And that was an issue. Now, technically, you're supposed to start with positive 75. Some people do one of two ways. This is, and the next thing too is that once you're dealing with 2's complement or any binary representation, you always take it up to any 2 to the n power. So you either show this as 4 bits, 8 bits, 16 bits, etc. Okay? So like in the case of 75, when we work out what the value is for 75, 2 into 75, this is 3, 15 would be 7, remainder 1. All right, 2 into 37 is, this is 1, this is 17, so this is 8, remainder 1. 2 into 18 is 9, remainder 0. 2 into 9 is 4, remainder 1. 2 into 4 is 2, remainder 0. 2 into 2 is 1, remainder 0. And 2 into 1 is 0, remainder 1. So the value that we got here was 7 bits long, right? 1, 0, 0, 1, 0, 1, 1. Okay? 1, 0, 0, 1, 0, 1, 1. You need to put that extra bit there, that 0 there, because we need to represent these values as 8-bit values. Okay? Now we can flip the bits to get the 1's complement. So you put 1's here and you say 1, 0, 0, 1, 0, 1, 0, 0. Okay, so we flip the bits. Did I do that? No. I feel like sorry. I made a mistake there. 1, 0, 1, 1, 0, 1, 0, 0. Okay, so we flip the bits so that we get the 1's complement. All right, and then we add 0, 0, 0, 0, 0, 0, 0, 1. And this will give us our 2's complement. Okay, so we end up with 1, 0 and 0, 0, 0 and 1 is 1, 0 and 0, 0, 1, 1, 0, 1. So this is the value that we get with the 2's complement working out. I was kind of lenient in correcting if you only use the 7 bits, but you need to make it into an 8-bit value. Okay?
Okay, sir.
Yes.
Yeah. All right. I know that some people would have worked out 75 like this. I saw that some people did this. 75, and you wrote out 1, 2, 4, 8, 16, 32, 64, right? And then you would take away 64 from 75. And you had a zero value for 32, you had 0 values at 16. They say 64 and 8 would be 72, so you have a value of 8 there, then 0 here, and 2 and 1, that's the 3 left, right? But this is really the recommended way here. That's really the recommended way to get your binary digit from a denary number. So I would recommend that you do this way, right? I think that CXC would be looking for this more than just you writing down this. All right, so that's just something to consider. Oops, what did I erase? Oh my gosh, I erased the whole page. Alright, I hit erase by mistake and everything on this page went. So, but at least we have it recorded. Now might be a good time to take a little 10-minute break. So we'll come back after 10 minutes and we'll continue the questions.